Recently, I've been thinking a lot about education and its importance in our lives. And I found three quotes which summarize my thoughts and ideas around the topic. Education is the most powerful weapon which you can use to change the world. The world as we have created it is a process of our thinking. It cannot be changed without changing our thinking. Thanks, Taylor. And she's right about things changing. Education is a tool for change. And so we're going to embark on a journey to learn about change. Or its more intimidating name, calculus.
What was that? The weather. Very peculiar, don't you think?
Yeah. Looks like the winds are changing.
Change is good.
Yeah, but it's not easy.
Deep down, calculus is the mathematics of change. It helps us understand speed, acceleration, how things change over time. We don't live in a static universe, so it's really important to understand what happens when we change things. Without calculus, we could not have sent a man to the moon, use our phones, or develop life-saving drugs and treatments. Calculus is the ultimate tool to describe and understand nature. It's a very intimidating topic when you first meet it, and I hope by walking through the history of the subject, meeting all the pioneers involved, and understanding their motivation and intuition, everything will start to make more sense. In the next few videos, we're going to be meeting the first ideas that kick-started the field of calculus and the way we think about change. Our journey into calculus begins on the floodplains of the River Nile. The ancient Egyptians were a great civilization, and their study of mathematics mostly focused on concepts in geometry, and they used this to build the magnificent pyramids. A problem they faced was the taxation of land for living and farming. They needed to know the area of shapes, like a rectangle or a triangle. But the shape that eluded them most, and many other mathematicians after them, was the simple and humble circle. And the area of the circle does give a strange result. You may remember from school that the area is pi r squared, where r is the radius. But what is this pi? There are many possible interpretations of pi. For example, the ratio between the circle's perimeter and its diameter. Or an infinite decimal with no repeating patterns. The story behind pi is very rich and quite fascinating, and this number appears in many unexpected areas of life and nature.
When I say I want, you say pie. I want
Pie.
I want
Pie. When I say yummy, you say pie. Yummy.
pie.
Yummy.
Pie.
Sorry everyone, but today we're just going to see how pi relates to ideas in calculus. The Egyptians had quite a good approximation to pi, 256 over 81. But it was really the Greeks who found an interesting way to calculate pi and the area of a circle. And the ideas they used formed the first building blocks and motivations behind calculus. So let's head over to ancient Greece to meet Thales, Pythagoras, and their contemporaries. A lot of great maths happens when we get bored and we just start to doodle. So that's exactly what we're going to do. So we start off with a circle, and we start drawing shapes inscribed within the circle. A square, a pentagon, a hexagon, and we keep on adding more sides. But life is too short just to keep on drawing regular polygons. So we take a minute and we look at our drawing, and we make an observation. It appears that the difference in area between the circle and our shape, i.e. the purple area, is decreasing as the number of sides increases. And it turns out this is true, and it's not too difficult to show. our shape starts to look more and more like a circle. This is the way the Greeks were thinking about the area of the circle and more general shapes. This strategy, often referred to as the method of exhaustion, is a key motivation behind calculus. By exhausting the area of the circle with regular polygons, we find better and better approximations to the area of the circle. It's important to note we can calculate the area of the polygons by breaking each polygon down into triangles whose area we can compute easily. So we now ask ourselves, could the circle just be a polygon with a large number of sides? After thinking for a while, it turns out this is not quite true. Okay, a little setback. Well, we know the area of the polygon gets closer and closer to the area of a circle as the number of sides increases, but never equals the area of a circle. So we muster up some courage and we ask ourselves, is a circle an infinite-sided polygon? And if you're confused, don't worry. It's a ludicrous question to ask, but also at the same time a very important one. Ludicrous because an infinite-sided polygon doesn't really make sense. What does that even mean? But it feels right in some weird, twisted way. The polygon looks more and more like a circle as the number of sides increases. This example highlights three of the most important concepts in calculus, and I'll let Paul McCartney talk about the first concept.
I'm getting closer. I'm getting closer to your heart.
Thanks a lot, Paul. In this example, we're looking at the idea of a limit. This concept of getting closer and closer to, but not quite reaching. We're looking at the extreme scenario. We're also looking at a big infinity, namely the number of sides of our polygon, and seeing what happens when we keep on increasing the number. We're also more subtly looking at a small infinity. And by this, I mean an infinitely small quantity. And here this is the difference in area between our circle and the area of our polygon, which keeps on getting smaller and smaller, but always stays positive. These three ideas form the building blocks of calculus, and we're going to spend a little time diving deeper into the first idea. This concept of getting closer and closer, but not quite reaching, might feel a bit strange at first. As you may wonder, why can't we just get there already?
Are we there yet?
No.
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 Are we there yet? Are we there yet?
Well, a lot of the time in mathematics, we deal with black hole scenarios, a case where we can never know exactly what is going on. In the method of exhaustion, this was when we wanted to look at a polygon with an infinite number of sides. To overcome this hurdle, we see what happens when we get closer and closer. As we approach the scenario, we want to see whether our investigation converges to something. We want to make a prediction of some sort. In the method of exhaustion, we see that the area of our polygons is a better and better approximation to the area of a circle. And if we could somehow conceptualize an infinite-sided polygon, then it would have the same area as a circle. So why do we expect this idea to work? We expect it to work as it's based on an idea of continuity. If I were to throw a ball lightly,
Pokeball, go!
after 1 second, I don't expect the ball to be on the edge of the universe. Common sense suggests the ball should be just a few meters away from me. In the same way, as we add more and more sides to our polygon, we expect that the area of our polygons will not blow up and give us a very different value to the area of a circle. So does this idea always work? Unfortunately, no. The idea doesn't always work, and we'll dive into this another time. The next video will be a story of great leaps and equally great losses. We'll see how another simple question leads to the field of calculus, and how one man was driven to murder to cover up the truth. Thanks so much for listening to the very end. I started making these videos because I wanted to teach mathematics through a more historical lens. By hearing the human stories behind the ideas, I believe the subject will just be easier to understand and just seem less intimidating. I'd love to hear your thoughts on improvements I can make, things you didn't like, and maybe things that you did like. You can reach out to me on email or via Twitter. Thanks for listening.